Hello, everyone. This is a short video that we want to have before lecture 3, in which we are going to run through some fundamental issues that I think it's easier for you to consume in advance and then bring to the lecture for some further unpacking. So the main business in here is that when we are faced with this huge amount of molecules that you now see come in a lot of different shapes and sizes and things like that, at some point we might like to find a trend. The finding trends is something that we discussed from the very first week of inorganic chemistry. It's the type of commonality that allows you to put a rule into the madness. So when faced with a lot of possible different molecules, a lot of possible coordination that add additional difficulties to the business, we might find ourselves with the question, do we have any similarity, dissimilarity? Do you have any classification for these common aspects? Mostly these classifications come in the shape of symmetry, because symmetry in itself is a concept that relates to trying to find a pattern in what you are faced with. So at different level of abstractions, you can just apply the concept of, is this symmetric or non-symmetric, based on a series of rules. So now in molecules, this is applied on the point of view that you are describing the symmetry of the molecules in terms of what are the features of the molecular structures. This will give you a lot of details on the bonding. It correlates with physical properties because it's something that arises from the physics of the molecule and will be reflected in some properties and some behaviors of the molecule, but this we will discuss more when we are in the live session of the week. So what do we mean when we say symmetry elements? We mean that the object that we are faced with, which in this case is a molecule, has a series of specific symmetry elements which can be a point, a line, or a plane, upon which you can apply an operation. If the object is symmetric in respect to the operation, then the object will be invariant after you're done applying the operation. So when we say element, we mean that you can have a point. So for instance, in this case, you notice here that you have this point in the middle. The object is symmetric in respect of the operation of inversion across the point. So if you invert everything that is on this side, you find yourself with everything that is on this other side, which means that the object has a point of inversion and is symmetric in respect to the operation of inversion. You can also have an axis. So you have a whole line around which the operation needs to be applied. And then the operation that you apply around an axis is a rotation. So if you can rotate the object and find it invariant, so if you spin this around, this will overlap with this will overlap with this, the thing that you get at the end is indistinguishable with the thing you started with. Or you can have a whole plane, so everything on a whole 2D surface gets the operation applied. So usually the operation that you apply across a plane is a reflection. So for instance, here you reflect off from one point to another across the plane. So usually you cannot have a molecule with a single symmetry element, a single operation. If there is a single symmetry element and a single operation, then the molecule will have a very, very little symmetry. If the molecule is really symmetric, then you start to add and add and add multiple one of these elements. Now, do we always have to list them constantly? Every molecule is unique, every molecule is a new business? No, not really, because all the symmetry elements that relate an object and can be found in an object can be collated in a mathematical group. So all these elements will be self-consistent, and the operation can be manipulated through the group. This is a very powerful thing. Group theory is a mathematical topic in itself. There are people that spend their whole life working in group theory. We don't have to know the whole group theory to know that we can use a symmetry group. So the symmetry group that we use in molecular symmetry is a symmetry group in which we collate all the operations that can happen in a molecule. And since all of these operations will leave at least one point invariant, could be more than one point, it could be a whole axis of points, it could be a whole plane of points, but there is at least one point that remains invariant upon application of all these operations. These groups are called point symmetry groups. Once you have these little collections, these little groups of things that can happen together, and if they happen, they will happen all together, then you can give them a name. And immediately when faced with the name of one of these groups, you will know something about the symmetry without having to do the whole derivation by yourself. Or in general, it would be a very useful classification that then will lead all the mathematics across coming around. So how do we actually describe this thing? There are different notations. Of course, different people will call things in a different way, but at the current state of the art, everyone working in molecular symmetry will use the Schoenfly notation. So this will describe the molecular symmetry, and if you find yourself faced with certain names, so you should recognize them for what they are. So, key point, this is for mathematical consistency. You can do nothing. There is the operation of doing nothing, which is called the identity, and it's defined with E. Then going a bit higher, you can do the rotation around an axis. You notate it with a C with this subscript n. Now the subscript n is not something that you use as it is, so you don't call this Cn. You specify which C you're talking about based on the fraction of 360 degrees that you are using. So if it's a 180 degree rotation, then the axis is a C2. If it's a 120 degree rotation, so 360 divided by 3, then the axis is a C3. If you have a 90 degree rotation, so 360 divided by 4, the axis is a C4. Going a bit further, you could have a whole plane of reflection that you will notate with a sigma. Now, the sigma as well can have a subscript. The subscript of the sigma is sometimes the most tricky part to understand. So you need to understand that you have a plane, but then the subscript will be dependent of where do you place the plane. So when you see the subscript, you will recognize which plane you're talking about. In particular, sigma v, it's a vertical reflection plane. You call it sigma v because it contains the main axis of rotation. So for instance, in a molecule like this, you will have two sigma v actually. So you will find them as sigma v prime. One of them, both of them will contain the axis of rotation, and both of them will leave the object invariant against the operation of reflection. So if the axis is here, a sigma v must contain the axis. The other option is having a sigma h. So the sigma h is perpendicular to the main rotation axis. So if you have a molecule like this, the rotation axis is going out of the plane because you want to spin around. Sigma h is the thing that is on the plane. So it is perpendicular to the main C. And then you have the other one, which is the sigma D. This is rather complex to visualize, but basically it's like a sigma V. But what you want is that you bisect between two C2 axes. So you can see here in the drawing, you have a C2 axis, a C2 axis, a C2 axis, and your sigma D is in between of this. So it's in a very specific position, not in a random angle between these two things, in the middle of these two things. So it's like this, but in a molecule that evidently must have more symmetry than this to allow this crossing over. So you can see this nice little star. You will notice that if you put one, then you must put also the others because they must be there by symmetry. Then there is the possibility of having an improper rotation. So in an improper rotation, you do two things at the same time. You turn around an axis and then you mirror across the plane. Note how this thing works. So basically you find yourself with a single element, which is the improper rotation thing. If this is the axis of improper rotation, what we expect is that a sigma, an S2, so something that turns around of 360 divided by 2, so 180, will basically be like combining a spinning around of 180. But if you do just a spinning around of 180, from this molecule, you find yourself like this. And then you must reflect across a plane that is perpendicular to this axis. So from this, if you reflect across a plane that is perpendicular to the axis that you used before, you end up to this one. Notice how this by itself is not a symmetry of the molecule. This molecule and this molecule are clearly different from each other. But when you combine this and this one together, then you have a symmetry of the molecule. Because if you do these two things together, you have a molecule that is fundamentally undistinguishable from the previous one. We labeled just to be able to track what we're doing. But if you take the indexes out, this and this are equal to each other. So that's the reason why the improper rotation exists as a unique element by itself. It's not the sum of two operations. It's an operation that must be performed all together. You can also have, for instance, in this case, you also have another sigma 2 in the same molecule, in which you put the C2 along the bond, so you can spin this around. When you spin this around, you find yourself like this. Being an S2, then you must have a plane perpendicular. When you reflect across the plane, then you find yourself with this molecule indistinguishable from this molecule, which is another improper rotation. And then your final option is the inversion, which is I. You flip diametrically across a point. So if you have a center of inversion, anything that is on one side will be flipped and thrown into the other. So this can interchange with this one. This can interchange with this one, and this can interchange with this one. And even if you look at all of them together, all of this should be able to go to the other side and the other way around. So each of the spots that you look into this molecule will have something across the center of inversion. Now, do we need to constantly derive everything that we find into a molecule? Not really. We assign the symmetry to a molecule by combing through the possible features that we see. So you only need the most prominent, the other one will follow. So you usually follow a flowchart. All the key symmetry elements are noted here. If you must notice if the questions that you have here are standing or not. If they are, you will fall into the right spot of your point group, and all of these things that you find here are actually the notation of the point groups in the Schoenfly notation. Funnily enough, a lot of these things will also correspond, no big surprise at the end of the day, to a geometrical shape. So in theory, if you find yourself with geometrical shapes will fall into this type of groups. And if you find the right projection of your molecule, sometimes you can kind of notice that it looks like one of these shapes, but the way you derive the symmetry is by using the flowchart. So how do we actually use the flowchart? We'll do a tiny assignment of the molecule of water. So we have our molecule. We look at the molecule in a proper arrangement. So if we don't draw it correctly, then you won't find the correct symmetry, but drawn correctly, then this is the geometrical arrangement. Off we go. Is the molecule linear? No, this is not a linear molecule. It's bent. Do you have 2 or more C and V with n higher than 2? Now, when you look at this symmetry, when you look at this arrangement of this molecule, if you want to flip this into this is 180 rotation. So it's a 1 C2 axis in the molecule. So by nature of this thing, there is nothing with a Cn higher than 2. So you can go off from here as a no. Do you have any Cn? Yes, we just say that we have a C2 rotation axis. Then once we are here, this can be a tricky question. You need to be careful while reading it. Select the Cn with the highest n. Are there any amount of C2 that are perpendicular to this Cn? So if you have the C with the highest n, which in our case is a C2, do you have anything that goes in perpendicular to this one, which is a C2? The answer in our case is absolutely not anything. So if you put it in perpendicular here, a C2 does not keep the molecule symmetric. If you put it in the other perpendicular, which is going out of the slide page, it's still not symmetric because you will spin this thing around and you will find yourself with this on top here, which doesn't make the molecule symmetrical. So the answer when we go here is no. Do you have any sigma h? Now, sigma h, by its nature, must be perpendicular to the main rotation axis, as we were discussing before. So you will have to have a plane of symmetry that goes out of the page. Now, that's not there because once again, it will flip this thing upwards and the molecule will look different. So no, you don't have the H mirror planes. The next question is, do you have any sigma B? So a mirror plane parallel to the main rotation axis. And unsurprisingly, when you go parallel to the main rotation axis, so either parallel on the plane of the page, then if you keep this thing on the plane of the page, then this is symmetric with the mirror. But most importantly, this is symmetric with the one that goes out of the page, because the real symmetry that you find is the one for which going out of the page, you get yourself a mirror going out. So yes, you do have those planes. One of them is here going out of the page, keeps these two symmetric. And the other one that follows, and it's a bit like a dull plane, is the one of the molecule. So since the molecule is on the plane, nothing happens to it. This leads us to this thing, which is, so you have sigma V prime. So since you're here, this is CNV, and you must assign the n. If you tell me CNV, it's not a space group, it's not a point group. So you need to give it the right n. So this is your highest order axis is an axis of order 2. So this is C2V. And that's the space group of water. You can also redo the point group derivation with other flowcharts, because sometimes you're like, oh, well, I don't like these questions. I would like different questions. At the end of the day, the concept is always still the same. So you will find yourself with maybe things that are worded differently, but the substance is still the same. I will give you, when we're doing point group derivation, I will give you these same flowcharts. So you can see here that by following the same path and the same questions, you land on the same type of point group. When we do this, more examples will follow in the live session. So now you know how the symmetry is composed of. You should remember the symmetry elements and what type of operations can you do. You should remember the concept of point group derivation with the flowchart. And in the live sessions, we'll do more examples, and you can note down any questions that you might have. We'll see each other on Monday 18th in the classroom.